Hey guys, today we are going to discuss buoyancy and the forces involved in something being buoyant. So, just to fire things off here, here are a few questions for you to consider as we're thinking about buoyancy and to kind of keep in your mind as we move along. So, the overriding one is, why do things float? So, what causes objects to float in water? Something kind of tied to this is that steel obviously has a higher density than water. So, how do boats float, considering boats are mostly made of steel? And finally, if you drop a rock into a river, does it fall as fast once in the water as it did when it was in the air? So, these are just some questions to kind of think about as we're figuring out the explanations to buoyancy here. So we're first going to talk about the buoyant force. So this is the force of buoyancy. And if we think about any volume of water and we separate out any individual portion of that volume of water, like this portion over in the diagram, any arbitrary element or volume within that fluid will be at equilibrium at its position within the fluid. And obviously, as we know, if we're at equilibrium, that means there is no net force acting on that system. So if we've separated out this portion of fluid right here from the rest of the fluid, its acceleration has to be zero if it's at equilibrium. And so its net force also has to be zero, right? Which means if we think about, there's going to be some weight that is pulling this arbitrary element of fluid down. That's its force of gravity, right? And so there has to be some force pushing back up. And that's what we call FB, or our buoyant force. So, and since we're at equilibrium, then those two things have to equal one another. So let's explore that. Just as a quick aside, particles in a fluid are not in a fixed position relative to one another. And so they're able to move independently. And obviously, we know that if we think about a fluid over here on the right, we think about a fluid as like one kind of thing, right? One liquid volume that all acts together. But really, it is something more like this: a bunch of independent particles that are held together by cohesive forces or intermolecular interactions that maintain them in one volume unless there is significant force pulling them apart. The internal interactions of the particles of the fluid will keep them together in the event that no external forces are imposed upon them. However, even though the particles move independently, the macroscopic behavior of the fluid will be a result of these internal interactions and any external forces acting on the fluid, meaning that the behavior of the fluid in its totality will be an effect of any net external forces acting on it. It is subject to Newton's laws, just like any other systems or objects in the world. All right, so let's go back to our buoyant force. So again, all of these particles act individually, but we can kind of think of volumes of fluid as acting together. And so if we think about our buoyant force, again, we have this arbitrary volume of fluid right here. And the buoyant force is the net upward force provided by a fluid over a volume that is displaced within that fluid. And it's going to be equal to the weight of the displaced fluid, again, because our net force equals zero. And so our buoyant force has to equal our force of gravity. And the upward pressure slash force on the bottom has to be greater than the downward pressure slash force up on the top because of the greater depth at the bottom end of the displaced volume. And we'll take a look at the pressure differential in just 1 second. But for now, let's just continue on with the equation we've set up already, which is, we know that our force of gravity that's equal to our buoyant force is also equal to mass times g, right? We know the force of gravity for any system or object equals its mass, the mass of that system slash object, times g, the acceleration due to gravity. And we also know that our mass for a fluid is related to its density and its volume. So we can find the buoyant force for any arbitrary volume of fluid by taking the density of that fluid times the volume occupied by that fluid times g, the acceleration due to gravity. All right, so let's take and make that equation again, but let's derive it a slightly different way. And let's, instead of considering the force of gravity acting on that arbitrary element of fluid, let's consider the difference in pressure from the bottom of the fluid to the top of that fluid. So in this case, we'll treat our fluid rather than just some random gelatinous volume. Let's treat it as a cylinder, all right? And the cylinder is going to expand some height, right? And the top of that cylinder is going to be some distance below the top of the volume of fluid that we're occupying, right? So that's H1 over here. And the bottom of that cylinder is going to be some distance away from the top of that volume of fluid, and that'll be H2. And we know that our buoyant force should be the difference. So the net force is being pushed upward on this volume should be the difference between the upward force coming from the pressure of the fluid on the bottom minus that downward force coming from the pressure of the fluid on the top, right? In addition to that, there will be the force of gravity, but we're not considering that right now. We're just going to find the buoyant force on its own. And remember, this buoyant force should equal the force of gravity. So in terms of the pressures, we have one pressure coming from the bottom. We're calling that F2. We have one pressure coming from the top. We're calling that F1. And this is just the pressure from the rest of the fluid pushing down or up on it based on the fluid pressure. So, and remember that last time we know that pressure equals force divided by area. And so if we want to find the force at our top position, or F1, we know that F1 is going to equal our pressure at that point times the area of the top of our cylinder over here. And we also found out last time that our gauge pressure at any point in the fluid will be equal to rho GH, right? The density of that fluid times G times H. And so we can substitute in for P, we can substitute in H1 rho G, and still we'll be multiplying that times the area. And we can do the same thing down here on the bottom for F2, right? And then we can substitute those terms in for F2 and F1 in our equation over to the left. So our buoyant force should equal the density of our fluid times A times G times H2, and that'll be the pressure at the bottom of this volume of fluid. And we'll subtract out the volume, the density of the fluid times A times G times H1, or the force at the top of our fluid. And so we pull out the heights there. We've got H2 minus H1 times our common terms, which are the density of the fluid times the area at the top and the bottom of the container times G. And obviously that H2 minus H1 really is just the height of the volume of this particular volume of fluid itself, right? The overall height of that cylinder that we've made within the fluid. And so if we separate out A times H, that is the actual volume of the fluid. So we get back to our buoyant force being the density of our fluid times the volume that we're occupying times G, the acceleration due to gravity, or exactly what we derived in the last slide for our buoyant force. And again, that should equal our force of gravity because because this volume of fluid is at equilibrium as it sits within the greater volume of fluid. That's our equation for buoyant force. It should equal the density of the fluid times volume times G, or rho Vg. So Archimedes' principle is exactly what we just derived, which is that the buoyant force acting on an object is equal to the weight of the fluid that is displaced by that object. So again, this is the weight of the fluid, not necessarily the weight of that object. And we can capture it with this equation up here, what we just derived, which is that our buoyant force equals the density of the fluid times V times G, or the mass of the fluid being displaced times G. And you'll notice, again, that we are not concerned with the density or the mass of the object itself. So for instance, if this is a copper or a brass cylinder that is placed into the water, you'll notice that its weight is larger than that of just the water, the volume of water that would occupy that space if the copper cylinder were not there. So in both cases, there's going to be some buoyant force, which is dependent upon, again, the density of the fluid times the volume occupied times G. So our buoyant force will be equal In both those cases, if it were just water hanging out there, the weight of the fluid will be equal to the buoyant force. But if we add in an object, then its weight will be different than the weight of the fluid. And depending on the difference, that will determine whether or not it will sink or will float. So whether or not the buoyant force will be larger or smaller, and thus whether the net force will be upward or downward. Buoyancy is the ability for an object to float in water, or, of course, any other fluid. So something will have a negative buoyancy if when we drop it in, it sinks. Something will have a positive buoyancy if when we drop it in, it floats or it moves upward towards the top. And something will have a neutral buoyancy if at whatever height it's at, it'll just stay there and just hang out at an equilibrium. So I've got two little density cubes here. They're density cubes because they're both the same dimension, but they have different densities because they're each made of different materials. So this one, the shiny one, is made of brass, whereas the wooden looking one is made of wood. And so when we place them into water, they're going to behave differently based on their two different densities. You'll be unsurprised to find that the density of brass is greater than that of water, and the density of wood, this particular wood, will be less than that of water. And so we can see these as two examples of positive and negative buoyancy. When we place the brass cube into the water, its force of gravity pulling it down is going to be larger than the force of buoyancy pushing it back up. And so, unsurprisingly, it will descend downward. That's an example of negative buoyancy. Negative buoyancy because overall its buoyancy is not enough to overcome its force of gravity pushing down, and so its net force will be in the downward direction or the negative direction if we define upward as positive. Meanwhile, the wood cube here has a lower density than water. And so if I push it into the center, then its force of buoyancy pushing up is greater than the force of gravity pulling it down. And so it just floats back up. Its acceleration is upward towards the surface of the water. And so that's an example of positive buoyancy, meaning the buoyancy provided by the water is greater than the force of gravity pulling the cube down. And so, again, both of them, because they have the same dimensions, will experience the exact same force of buoyancy when they're submerged in the water, right? They have the same dimensions, so they're displacing the exact same amount of water, so they'll experience the same force of buoyancy upward. However, because they have different forces of gravity pulling them down, the brass has a greater force of gravity. It'll have a negative buoyancy, meaning its buoyancy cannot overcome its force of gravity, whereas the wooden block has a positive buoyancy, meaning its force of gravity is less than the force of buoyancy, so it'll get pushed upwards. All right, so let us run a few practice problems. Our first one, let's consider a pufferfish. So he's swimming around and he gets spooked by a hammerhead shark and he puffs up to his full size, roughly a sphere with a radius of 12.5 centimeters. So we'll write that down. We got a radius of 12.5 cm, which of course is 0.125 meters. And furthermore, we know that the volume of a sphere is 4/3 pi r cubed. So we'll table that for a moment. And if the pufferfish now has neutral buoyancy, we have to figure out what the pufferfish's mass is, right? And we know that if he's got neutral buoyancy, that means he's floating and he's at equilibrium. So his force of gravity is equal to his force of buoyancy. Right? So his force of gravity is going to be his mass of the pufferfish, let's say that's MP, times G. And the force of buoyancy, we now know, is the volume of the fluid times the density of the fluid times G. Right? So the density of the fluid times the volume that he's occupying times G. So the G's actually cancel out here, right? And we end up with the mass of the pufferfish just equals, in the case that he has neutral buoyancy, where his force of gravity equals his buoyant force, then his mass is going to equal the density of the fluid he's in times the volume of that fluid that he's occupying. All right. So again, we know the density of water, and the density of water is 1,000 kilograms per meters cubed. And we also know the volume for a sphere is 4/3 pi r cubed. And in his case, the r is 0.125 meters. And then we will cube that. And if we run those numbers, we should end up with 8.18, and this would be kilograms, because our meters cubed on the bottom of our density canceled out with our meters cubed within our volume, for our units for volume. Right, so with 8.18 kilograms is our mass of the pufferfish. All right, so for next problem, we're going to toss some pennies into a pool, and each penny has a shape of a little flat cylinder, right? And we're given the dimensions of a penny. The dimensions of a penny are, it has about a diameter of 19.1 millimeters, or a D of 0.0191 meters, and it has a thickness of 1.52 millimeters, which I'm just going to call its height. Its height equals 0.00152 meters. So we can find some more dimensions for the penny. Let's first think about the area of its face. So the area of its face is going to be that of a circle, right? Which is pi r squared, or pi times half its diameter squared. And so that area is 2.865 times 10 to the negative fourth meters squared. And to get our volume for the penny, we want to take that area of the face and multiply it times its height. And if we take the 2.865 times 10 to the negative fourth and multiply that times the height of the penny, or 0.00152 meters, then we should get 4.355 times 10 to the negative seventh meters cubed. All right, so that's the volume of our penny. And furthermore, let's think about one last thing here in terms of the dimension of the penny, which is we'll eventually want the mass of our penny. And the mass of our penny equals the density of the material the penny is made of, which we'll call copper. Modern day pennies are only like 70% copper, the rest is zinc, but we'll just pretend it's entirely copper, because our problem here gave us the specific gravity of copper, not the specific gravity of copper and zinc. So it would be so our mass of the penny will equal the density of our penny, the material of a penny, times the volume of the penny, right? And if we take that and we try to figure out what our density of copper is, we weren't given our density of copper, but we were given the specific gravity of copper. And remember, the specific gravity of any substance is the density of that substance divided by the density of H2O. And so what that tells us is that the density of copper equals the specific gravity of copper times the density of H2O. And so if we substitute that in to our mass equation over here, the mass of our penny equals the density of copper, which is the specific gravity of copper times the density of H2O, and then times the volume. All right, so we're going to table both these two equations, our equation for volume and our equation for mass, for 1 minute. And let's think about the forces acting on our penny. So our penny is getting pulled down by the force of gravity, of course, since it is within the gravitational field of the Earth, and it's getting pushed back up by the buoyant force from the water. All right, so that buoyant force I drew as smaller than the force of gravity, because if you've ever thrown a penny into the pool, you know that it's going to sink. And so the force of gravity is going to be larger than our buoyant force. And this means that our net force will equal our force of gravity minus our buoyant force. And our net force, of course, will be in the downward direction. So we can start plugging in numbers over here. We know that our net force equals our mass times the acceleration. Our force of gravity is mass of our penny times g, the acceleration due to gravity. And we have an equation or a term for buoyant force we can substitute in here, which is the density of our fluid. In this case, that's H2O times the volume that the penny occupies times g. And if we want to solve for acceleration, we divide everything by mass. And so mg divided by mass would just be g minus our density of H2O times the volume the penny occupies divided by the mass of the penny times g. So what does this tell us? This tells us that the acceleration that the penny will experience will be equal to gravity, right? Which is the acceleration it would experience if there was just a force of gravity pulling it down. It would be 9.81 meters per second squared. Subtracting the amount of acceleration that the buoyant force is taking away from that acceleration due to gravity, right? Which we can again find with that second term, that the density of H2O times volume divided by mass times g. And then last thing is we want to substitute in that equation for mass over there. So we get this. So let's substitute in for mass. We get their acceleration can equal g minus rho H2O times v divided by, let's sub that in for mass, Sg of copper, our specific gravity of copper, times rho H2O, or the density of H2O, times v, the volume occupied by the penny, times g. So and then we can cancel out the terms on the top and the bottom, which is volume cancels out, and so does density of H2O. So look at that. We get a very nice simple term in the end here. Our acceleration equals g minus g divided by the specific gravity of copper, or g minus g divided by the ratio of copper's density to water's density. So we can plug in some numbers here, and what we get is 9.81 meters per second squared minus 9.81 meters per second squared divided by the specific gravity of copper, which was 8.96, which gives us an acceleration of 8.715 meters per second squared. And so our acceleration, when we include this buoyant force, when there is a buoyant force of water pushing back up on our penny, will obviously be less than that of the penny in free fall in the air, right? And now that we have our acceleration here, we can take and we can run the numbers. We can find, given that acceleration, and given that we know how much distance that penny has to go, right, which is a delta x of 10 meters, and we've got an acceleration of 8.715 meters per second squared. We just need one other variable in order to use our motion equations, right? And if we assume that once the penny is at the top of the pool, it is at an initial velocity of 0 meters per second, then all we need to do is use our kinematics equation to find our amount of time that it would take for that penny to reach the bottom. And we should find that the time, if you run the math, should be 1.51 seconds. So please take a minute to verify that result yourself. But this is how we would find our acceleration for that penny. And then once we have acceleration, then obviously we know how to do all of our kinematic stuff. All right, so it says it would take, so we just calculated it would take about 1.51 seconds for a penny to drop through a 10-meter deep pool. Remember, 10 meters is about 30 feet, so I don't know if you've ever been in a pool that large, but think about, does this make sense with your experience of dropping pennies or other items in a pool? What is our model leaving out? So why don't you take a moment to think about that and come back. And really what we're leaving out here is that just like air, water and any other fluid is also going to exert a drag force as an object moves through it, right? So really, if we made a free body diagram for a penny, we got the force of gravity pushing down and our buoyant force pushing up. But we're also going to have some drag force pushing up. And as the And as the velocity of the penny increases, that drag force is going to increase and increase. And that's why penny is going to move slower than we just predicted, right? So for a penny to move 30 meters through the volume of a pool, it's probably going to hit its terminal velocity in water pretty quickly. And that's why it's going to seem like it floats a lot slower than 1.51 seconds would take for it to get to the bottom. All right, and then we've got this last problem here. But we're going to take a look at this in class. All right. So if you wanted to, you could think about this right now and you can consider it. But we will look at this all together in class as we further discuss buoyancy. Thank you for paying attention to this lesson.